This contraption here is called a ballistic pendulum. It's used to show how first we can have an interaction where we really focus on conservation of momentum, and then there's follow-up interaction that's based on conservation of energy. Well, technically both conservation of momentum and conservation of energy are holding the entire time. When it comes to actually analyzing a problem, sometimes we care about using one set of formulas, and another part we care about using a different set of formulas. So this is how this thing should behave. Press this button. Dang it. I'm going to reset it. Let's assume that when this thing launched out, the ball went into this, and then it caused this entire thing to fly up to some new height. So what's happening here is there's some interaction where the ball flings into the cup, and they undergo collision, and then as a unit they begin moving forward. And then as they fly forward, because of this setup up here, it causes it to swing and go up to a certain height based on how much energy or how much kinetic energy the whole system had due to that interaction that happened here. So, showing that as a diagram, it's flying, our projectile has some mass and it's moving with some velocity, and it impacts and embeds itself in another piece of mass that's just sitting here hanging. So our first set of before and after situations are just before the bullet puts itself inside of the object that it hits, and just after those things have collided and embedded each other. So the big block hasn't necessarily, it's the moment after the two things have come together and begin to move. So it hasn't actually swung up yet, but in this after situation, both of the masses are combined and they are in the process of beginning to move this way, conserving momentum along this direction. Then what we can say is, well, now I have a big chunk of mass and it's moving with some velocity thanks to that collision that occurred. Therefore, it has kinetic energy. So this entire system must have a certain amount of kinetic energy. And later on, that system has swung up to a new height. And luckily for us, with conservation of energy, all we care about is, well, what are the initial kinetic and potential energies, and then what are the final kinetic and potential energies? Because it turns out by knowing these, we don't really care about how the block got from here to there. We only care that, well, the block had a certain amount of kinetic energy, and later on, by raising itself in the gravitational field, it stored a certain amount of gravitational potential energy. And the amount of potential energy it stored had to be equal to the amount of kinetic energy that that was available to get converted into that potential energy. So to break these two statements, the one about conservation of momentum and then looking at conservation of energy into formulas, here we look at conservation of momentum first. We write down a momentum term for both particles in the before and in the after condition. In this case, things simplify because initially this mass isn't moving. So its momentum in the initial condition or in the initial part is 0. The bullet is flying in with some, just some initial velocity. After they've impacted and are in the process of beginning to move forward, well, they're stuck together. So that means they share a common final velocity. So I'm going to replace that common final velocity with just a large v. So bullet flies in with some velocity, and then after the collision, the two objects together are trying to begin to swing away with some new velocity. Then we look at, okay, now we're done with the momentum part of this. We care about the conservation of energy as we go from here up to here. So we write down our full conservation of energy. We'll assume that there's only kinetic and potential energies in this system. So all the initial kinetic plus the initial potential equals the final kinetic plus the final potential. Well, what's the initial kinetic energy? Well, here we care about, at this moment, these two pieces of mass are moving together with some velocity. So 1/2 times that total amount of mass times that velocity squared. The final kinetic energy, well, we're going to assume this thing swings up to its highest point, and it's as high as it can go. Now, in the case of this machine here, the little thing that didn't work when I tried this earlier is there's a little latch here so that this thing, when it swings up, it can catch, and so we can actually measure how high it goes. But in principle, if this was just a hanging pendulum and this piece wasn't here, then we'd fire this thing. This would now have a certain amount of kinetic energy. It would swing up to some maximum height, and then it would swing back down again. So, because that amount of kinetic energy was converted into potential energy, and that potential energy would be converted back to kinetic energy as it swung back down. It's not really designed for that, because then it would just bang against this piece, and then it stops behaving as this ballistic pendulum. So, since it's reached its highest point, we know the kinetic energy would have to have been 0. Then we say to ourselves, well, let's set this height that it's originally just hanging at to be the height 0, and it swings up to a height h. And so because of that, the initial potential energy, the total amount of mass times g times the height h is located at, that's 0, because that height would be considered 0. And then it's come up to a height that we're going to call h. So the total amount of energy there is the sum of the masses. Mass times acceleration due to gravity times that height. So now we have an expression for what that velocity of the two things moving together would have to be in terms of how high it goes. So now we have to bridge all the way at the end to all the way at the beginning. Well, note we can take this expression and rearrange it so that we get the incoming velocity of the bullet as a function of the masses and this velocity of the two things moving together right here before they are actually swinging up. This expression also gives us, hey, those m1 plus m2s cancel out on both sides, and I can solve for that large v, that large velocity. And in fact, when you do that, it turns out that expression is just square root of 2gh. Again, the masses cancel out on these. And so now, for this system, it turns out there's a nice direct relationship between how fast something is going, how fast this little piece is going, and how high it will swing up to based on what the two masses are. So, just an example of a system where we have both conservation of momentum and conservation of energy. Both of those pieces came into play at different points in analyzing this setup so that it can give us a single coherent expression that tells us everything about what we ultimately get based on what we started with, or alternatively, if we see that this thing swings to this height and we know that it has these certain masses, how fast was this traveling in order to make this observed behavior happen?